Good day, good evening, everyone. Today, I'm presenting an overview of database system architectures. Let's dive into the essential of database management systems and their structural foundations. Let's get to the heart of the presentation, database system architecture. We will examine four key types: centralized systems, client-server architecture, parallel systems, distributed systems, and also network type that we use for database systems. Each represent a different approach to managing data influenced by factors like scale, user needs, and hardware capabilities. We will also briefly cover network types as they play a critical role in how these systems communicate. This overview sets the stage for understanding modern database design. First up, centralized systems. These are the simplest form of database architecture and running entirely on a single computer system with no interaction with external machines. Think of a standalone desktop application. Everything from processing to storage happens in one place. They can be general purpose, it means supporting either a single user or like a personal finance application or multiple users such as a small office server. While easy to manage, their limitation is scalability. They are not built for large distributed workloads. Here is a visual of centralized computer systems. Picture a single machine with a monitor, keyboard, printer, mouse connected to disk for storage and a memory unit, all coordinated by a disk controller. So centralized computer, we have CPU or central processing unit, also called as central processor, main processor, or just processor. It's a kind of electronic circuitry that execute instructions comprising a computer program. Then we have this controller here. This controller provides an interface between the disk drive and the bus connecting to the rest of the system. And also it enables the CPU to communicate with the hard disk, or you can say USB or other disk drive that we have. Then we have USB controller here. It's a kind of chip or a device, and that is used to allow the computer to communicate with the USB device. Then we may have GPU, or we can say video card, graphical adapter, display adapter, or something like this. This is the expansion card which generates a feed of output image to display devices. But recently we have more strong GPUs that they are using for heavy machine learning models. Moving to the client server, it's a kind of a setup in complexity. Here, a powerful server like, for example, you can say Oracle server or Microsoft SQL server, they are employed to handle requests from multiple client machines. Imagine a web application, like for example, your browser, and we call it as a client. It doesn't matter your computer, tablet, iPhone, or anything. They send a request to a server, and then the server process it and send back data, for example, web page. This division of labor allows specialization. Server focus on heavy lifting while clients manage user interaction. It's a foundational model for any enterprise system today. So client server is a distributed application structure, and we partition tasks or workloads between the provider of resource or service that we call it as servers and server requests that we call it as clients. Client and server communicate on a computer network on separate hardware, but both client and server may reside in the same system. A server host runs one or more server programs which share their resources with client. A client usually does not share any of its resources, but it requests content or service from a server. Clients therefore initiate communication session with servers with await incoming requests. Example of computer application that use client server is like email, network planning, or Google server that you use. All of them, they use client server. In the client server systems, database functionality is split into two distinct roles, back end and front end. The backend running on the server. And this backend is used to manage the core database operations, storing data, processing queries, and ensuring consistency. The front end is on the client side and is used to handle what users see and what they can do. These two communicate via interface. Typically, you can say SQL for direct queries or an application program interface like API for more complex interactions. This separation enhances modularity and allows independent upgrades to either end. For example, for this SQL API that you can see here, application program interface, these are used to interact with like our tables and data into the system that we have. So front end, what we can see, back end, what we cannot see, and interface in between. Let's zoom into the backend, also known as server-side programming. This is where the database lives, storing data in tables like customer record or product inventories. It manages access structures such as index to speed up search. It also evaluates and optimizes queries. For instance, finding the fastest way to retrieve all orders from last month. Concurrency control ensures multiple users do not overwrite each other's changes. And recovery mechanism restore data after crashes. Backend is the engine room of the system. Now, the front end, or we can say client-side programming. This is the user's window into the database. Everything user can see and interact with. It includes tools like forms for data entry, report writers for summaries, and graphical interfaces for navigation. For example, in an online store, the front end displays product listing and sends your order to the backend. It also fetches data from the server, stores it temporarily for display, and ensures a smooth, responsive experience. User experience hinges on this layer. Why choose client server? It offers compelling benefits. You get better functionality for cost. Servers can be optimized for heavy tasks while clients remain lightweight. It's flexible. Resources can be placed where they are needed most, like putting servers in the data centers. User interface improves with dedicated front-end design. And also, maintenance is simpler. Update the server without touching every client. Think of a bank's online system, efficient, scalable, and user-friendly, all thanks to this client-server model. Within client server, servers themselves have specialized architecture. So we have transaction servers and data servers. Transaction servers power relational databases, like those managing banking transactions, focusing on structured data and SQL. How they work, they use a structure that allows us to identify and access data in relation to another piece of data in a database. Often, data in relational database is organized into tables. On the other side, we have data servers. Data servers, meanwhile, support object-oriented databases ideal for complex data like multimedia or other type of data. So these object-oriented databases, or in short, we call them as OODBMS, or we can say Object Database Management System, Object Database Management System, is a kind of database that is based on object-oriented programming, what we have in C++, Python, Java. The data is represented and stored in the form of objects. So these OODBMS are also called as object database or object-oriented database management system. Each type tailors its approach to the database need, balancing speed, structure, and flexibility. We will dive deeper into these next. Let's define a transaction, a critical concept in databases. A transaction is a single unit of work that accesses and updates data, ensuring all steps complete or none do. Take transferring $50 from account A to account B. First, it reads A, subtract $50 from A, writes the new balance, read B, add $50, write B, update B. If any step fails, say for example a power outage, the system rules back to prevent inconsistency. This automaticity is what keeps database reliable. Transactions come in two flavors: local transactions and global transactions. Local transactions access data at the site where they start. Think of updating a local inventory database. On the other side, global transactions span multiple sites, like syncing stock across warehouses. Challenges arise here. Hardware failure or crashes can disrupt execution, and concurring transactions, like two users updating the same record, need careful coordination to avoid conflict. These issues drive much of database system design. A transaction has several states: active, partially committed, failed, aborted, and committed. A transaction lifestyle has five main states. It begins with active, executing its steps. Once finished, it is partially committed. Changes are made but not yet permanent. If an error occurred, it fails and may be aborted. Rolling back changes. Afterward, it can restart if the issue is fixable or be killed if not. Successful completion leads to commitment, locking in the changes. For example, a failed bank transfer aborts to avoid partial update, ensuring data integrity. Transaction servers, also called as SQL server or query servers, centralize transaction processing. By definition, a transaction server is a specialized type of server that manages the data operation of software-based transaction or transaction processing. These transaction servers are used to manage application and database transactions on a network or on the internet within a distributed computing environment. In here, clients send requests to the server, say an SQL query like select balance from accounts table. How? Via remove procedure calls, we call it as RPC. The server executes these, often bundling multiple calls into a single transaction for efficiency, then ship results back. Picture an e-commerce checkout. The server validates stock, processes payment, and confirms all in one transaction. This model scales well for relational data. So we are about to explore the process powering transaction servers. This slide is a placeholder, but think of it as the behind the scene machinery. Multiple components working in harmony to handle queries, ensuring consistency and recover from failure. Let's break it down. So in here, for example, we have ODBC. So we have user process, user process, user process here, or we may have ODBC or JDBC. This ODBC, it means Open Database Connectivity. It's a kind of SQL-based API created by Microsoft, and this is used by Windows software application to access databases via SQL. On the other side, we have JDBC. It's an SQL-based API created by Sun Microsystem to enable Java application to use SQL for database access. These APIs provide communications between an application residing on a client machine and a data source residing on the same client machine or another server computer. So here we have processes coming from user process. It means executing program. So all are on a server or even on the client side. So maybe processes are divided into some thread. The basic unit to which the operating system allocates processor time. Then we have log buffers that records to log record buffer. Then we have here process monitor process. These are used to monitor other processor and takes recovery action if any of the process fails. Then we have, for example, checkpoint process. These perform periodic checkpoints. So all together work to complete a task. ODBC, a key tool for a transaction server is ODBC, Open Database Connectivity, and this is a kind of Microsoft standard. This ODBC is a C-based API and lets client connect to server, send SQL requests, and receive results. It is designed for relational databases and it is fast and interoperable. Your applications can talk to Oracle or SQL Server via one interface. For Java developers, JDBC offers a similar approach. ODBC's universality makes it cornerstone of client-server communication. Inside the transaction server, multiple processes collaborate. When we say multiple process, again, a process is simply an executing program. Server processes receive and execute queries, often multi-threaded, to handle several tasks at once. Imagine processing 10 customer orders at the same time. Then in here we say thread. Thread is the basic unit where operating system allocates processor time to execute that one. Then we have here log manager. A log manager prevents conflicts, like two users editing the same record. The database writer continuously saves changes to disk, ensuring durability. Together, these form a robust system for managing high query volumes. More processes round out the system. The log writer records every change to stable storage, critical for crash recovery. Think of it as a transaction diary. A checkpoint process periodically snapshots the database, speeding up recovery. Then we have the process monitor process. These watch for failures. If a server process crashes mid-transaction, it aborts and restarts it. This teamwork ensures reliability even under heavy loads. Data servers take a different tack, thriving in high-speed LAN where clients match server power. Unlike transaction servers, they push full backend functionality like query processing to clients. This suits compute-intensive tasks like analyzing large datasets. However, it raises several issues. Should data ship by page or items? How do we handle locking? And what about caching and also log caching? These trade-offs shape data server design. Consider shipping. We have page shipping and item shipping. Page shipping sends whole data page, reducing message overhead. Think sending a book instead of chapters. What is the meaning of page shipping? It's the unit of communication for data and can be coarse granularity, such as a page, or fine granularity, such as tuple or an object. So in the case of item shipping, it sends smaller units, increasing message but offering precision. Prefetching related items with page can boost efficiency. Logging, though, is trickier. Requesting logs from the server our network adds delay, making coordination a bottleneck in high traffic scenarios. Caching is a game changer for data servers. Data caching means data that are shipped to the client on behalf of a transaction can be cached at the client even after the transaction completes if sufficient storage space is available. In other words, client can store data and logs locally between transactions, speeding up access like keeping a book on your shelf. Cache coherency checks, often tied to log requests, ensure data is not stale. Log caching lets client reuse log without server calls, with the server recalling them only for conflicts. This mimics the escalation but persists across transactions and hence optimizing performance. So, in the case of log caching, if the use of data is mostly partitioned among the clients, with client rarely request data that are also requested by other clients. Logs can be also cached at the client side. Parallel systems is the another architecture for databases. Parallel systems leverage multiple processors and disks connected by fast networks in order to boost performance. So in here we have coarse-grained parallel machine. Coarse-grained systems use few powerful processors, but fine-grained parallel machines deploy thousands of smaller ones. Think of a supercomputer compared to a cluster computer. So this coarse-grained description of a system regarded as large subcomponents. On the other side, fine-grained description regards smaller components of which the larger ones are composed. We measure success via throughput or response time. Throughput, task completed over time, and response time, how fast one task finishes. So, in definition, throughput is the number of tasks that can be completed in a given time interval. On the other side, response time is the amount of time it takes to complete a single task from the time it is submitted. Parallelism powers everything from scientific simulation to big data analysis. Next, scale up splits two types: batch scale up and transaction scale up. Batch scale up handles a single large job, like a quarterly sale report, scaling both system and task size, ideal for decision support or simulations. Then, for transaction scale up, it supports many small queries like online purchases with more users and a larger database on a bigger hardware. Both batch scale up and transaction scale up aim for efficiency. However, transaction scale up mimics real world multi user systems like busy e commerce platforms. Parallel and distributed systems rely on interconnected networks. So here we want to talk about network topology that are used for parallel and distributed database architecture system. What is topology? Topology is the layout of links and nodes, determines speed and scalability. A poorly designed network can bottleneck even the best hardware. We will explore three common topologies next, each balancing cost, complexity, and performance in unique ways. The first one is the bus topology. Bus topology uses one shared communication line, as you can see in this image, like highway all computers tap into. Data flows to and from this bus, connecting processors and disks. It's simple and cheap, perfect for a small setup. But as parallelism grows, say adding more processors, the bus gets congested. Bandwidth limits make it impractical for large-scale parallel systems. Then we have mesh topology. Mesh topology arranges computer in a grid, like a city block layout. Each node connects to its neighbor, and as the system grows, so do the links, offering better scalability compared to the bus topology. Communication is more direct, reducing delays. Think of a data center with rows of servers. Mesh keeps data flowing smoothly as the grid spans. As you can see here, every system is connected to another one using a communication link. The next one is hypercube topology. It's more abstract. In here, nodes are numbered in binary, as you can see here. These are the nodes and these are the links. And they are connected to each other if their binary numbers differ by 1 bit. As you can see here, these two are connected because only 1 bit is different. These two are connected because 1 bit is different. This one connected because 1 bit is different. Like a 3D cube for 3 dimensions with 8 nodes and 3 links. So we have dimension n, 8 nodes, and then link per node 3, longest path is 3. Path is a set of links. This minimizes the longest path between nodes, cutting communication delays. In a database cluster, hypercubes speed up data sharing, making them ideal for high-performance parallel systems. Parallel databases come in 4 flavors: shared memory, shared disk, shared nothing, and hierarchical. So, what is shared memory? It means memory is shared among them. So, shared memory gives all processors access to one memory pool via a bus or a network. Communication is lightning fast. Processors share data instantly, like co-workers in one room. But scalability caps at 32 or 64 processors. Beyond that, the bus saturates and contention slow everything down. It's great for moderate sized systems. Share this system, let all processor access all disks, as you can see here. They can access all these through a network, but each has its own private memory. As you can see here, each process has a memory. This offers fault tolerance. If one processor fails, others can still access data. The catch? The disk interconnection becomes a bottleneck as traffic rises. Picture a shared filing cabinet. Everyone can use it, but only one at a time grabs a file efficiently. Then we have shared nothing. It means every system has its own storage and memory, right? This is the minimalist approach. Each node has its own processor, own memory, and own disk, with no shared resources with others. Systems like Teradata or Oracle Ncube use this for massive scalability. Add nodes and capacity grows linearly. Data stays local, but non-local access requires network calls, raising communication costs. It's like independent office collaborating via email, efficient but slower for remote tasks. Then we have hierarchical. It's a kind of hybrid of all share nothing, share disk, and share memory. We combine all together, as you can see here. Hierarchical architectures blend the best of all worlds. At the top, it's share nothing. Nodes are independent. Within each node, shared memory or shared disk setups optimize local performance. This hybrid reduces programming complexity with virtual memory tricks, making large systems manageable. Think of a company, headquarters coordinate, but branches operate semi-independently. Distributed systems takes us beyond one location. Data spreads across multiple machines, sites, or nodes, and they are connected by a network, serving users everywhere. Imagine a global company with databases in New York, Tokyo, London, all accessible to employees. This scales beautifully but demands sophisticated coordination to keep data consistent and available. Distributed databases come in two types: homogeneous distributed system and heterogeneous distributed systems. Homogeneous ones run the same software and schema across sites. Partitioning data for efficiency, users see one unified database, hiding the complexity. On the other side, for heterogeneous database, these heterogeneous databases integrate different systems, like merging a legacy payroll app with a modern CRM. The challenge is interoperability, but the payoff is leveraging existing infrastructure for new capabilities. Distributed systems balance trade offs. Sharing data lets remote user access records, like a London employee checking New York inventory. Autonomy keeps local sites in control of their data. Redundancy boosts availability. If one site fails, others step in. But this comes at a cost: complex software, higher bug risk, and processing overhead. It's a powerful but demanding approach. Implementing distributed database tackles big challenges. Automaticity ensures transaction complete fully or not at all, often via two-phase commit protocol across sites. Distributed concurrency control prevents conflict over shared data and data replications. Copying data to multiple sites, it means, boosts speed and reliability, but also requires sync mechanism. These are the nuts and bolts of distribution. So we come to the network type. Local area network is one of them. Networks underpin all this. Local area networks, or we call it as LANs, connect processors in small areas, like a single office or campus. They are fast and low latency. They are perfect for localized parallel or client server setup. Think of a university library system. All terminals tie into one fast LAN for quick access. Then we have a storage area network, or SAN. These link multiple computers to vast storage arrays, mimicking shared disk system on a grand scale. These SANs are built for high-speed access to centralized data, like a data center serving dozens of servers from one storage bank. These SANs excel in environments needing massive and reliable storage. And finally, WANs, wide area networks. These span continents, connecting processors over vast distances. They power distributed systems like a global banking network linking branches in many countries worldwide. They are slower than LANs, local area networks, due to the distance. They rely on robust protocols to ensure data flows reliably across regions. Okay, to close, we have journeyed through database architecture, from the simplicity of centralized system to the complexity of distributed networks. Each design tackles unique challenges: scale, speed, reliability, and coordination. These concepts drive everything from small apps to global enterprises. Thank you for your attention. I love to hear your questions or insights by leaving a comment below this video. See you in the next lecture.